Okay, so before the break, we were looking at two's complement numbers. That's how computers deal with negative numbers. That's kind of an important one. So, well, because that's how computers actually deal with negative numbers. They have the integer representations, and then two's for positive numbers, and two's complement of that integer to represent a negative number. And then we can simplify our math down to just one operation, and which also allows us to compare, because then we can do that one operation and we either have, when we compare two numbers, we either have a zero, they're the same number, or they're equal, or one of them's bigger than the other. And two's complement gives us a way to do all of that in one type of circuit. So that's what machines actually use. There's a couple other bits of binary on our major learning objectives. So we need to talk about these quick. These will go quick. One of them will go quick because it hasn't really been used in 30 years, but it's on the major course learning objectives. So we'll at least talk about what it is and what we use nowadays instead, which should make even more sense to you. And the other one is kind of complicated, so we'll just kind of introduce it. It's another one that machines actually do, but it's more for something electrical engineers have to study. So we'll get through all our binary stuff, and then in the next section, introducing selection structures in code, we'll go quickly. So it looks like we'll be able to get through all the module 2 stuff, but I'm gonna give you more than 2 days to do the homework. Since we're just now getting through it today, that'll push the due date back 5 days, which we count that out, that'll be Friday, right?
Well, what'd you say?
Since we're just now getting through the material, there's going to be a couple days to do the homework. So I'm gonna.
Oh, so for this module?
Yeah, just this module.
Okay. Thank you. Yeah, I've been. My birthday's coming up, and so and then.
Oh yeah. That's gonna be a rule of thumb, Keegan. If I'm not gonna have the homework due until after we've covered it in class, and I know people have jobs and other things. So I want to give at least 5 days. Oh, so that'll be Friday night. So is that okay to everybody here? So I have another comment about that for the video. That'll give 5 days for a couple of the classmates.
That's fine for me.
Okay.
Extra time is better.
Okay, and for a couple of classmates that'll be watching the video later, for Bradley and Dakota, will Friday night be okay? If you need to make that Saturday, that's fine. Because for the rest of you all, that's some of your classmates have 9 to 5 jobs, so they can't be here at 1 o'clock in the afternoon. So they'll watch this video this evening when they get home from work. And if they have 9 to 5 Monday through Friday, I have no trouble pushing that back to Saturday. If you're one of the people that has to do your homework on the weekends. Just let me know, but I will push that back to Friday night so that we have time to cover it. And for those who work Monday through Friday during the day and are probably exhausted when you get home at 6 o'clock in the evening, if you need to do that on Saturday instead of Friday, I'll be fine with that. Just let me know. So 2 more things about binary to cover. The first one is binary coded decimal. Well, we're representing our numbers, right? The machine doesn't know what they are, so we're just doing a representation. So sometimes you might have really big or really small numbers. For example, there's a website we can go get pi to over 1 trillion digits. That would give us some accuracy on some really big calculations. The sort of calculations we would want a machine to do, because we're certainly not going to do that by hand, right? We have lots and lots of digits, but really in that case, doing that as a power of 2 would take a huge binary number, right? So alternatively, we can just store it as a string of characters. Store as a string and calculate the value at runtime. That string of characters, each one of those is going to be in a certain spot, right? We have the 3 in the 1 spot, the 1 in the 10th spot, the 4 in the 100th spot, and so on and so forth. They'll be way too big, but we can quickly do that calculation for each one of those columns, and then put the end result back together. So we could just do it symbolically. How about that word here? String or symbolically. Are normal symbols for representing numbers. In which case, we don't need all those bits. We could do all of our digits in 4 bits, right? Well, if we did 3 bits, 2 to the 0, 2 to the first, 2 squared, 1, 1, 1, 4 plus 2 plus 1 gives us 7. So 3 bits isn't enough. If we add that 2 cubed, 1 plus 7 plus 8 more gives us 15. That'll cover our 9 digits, 0 through 9, right? So we could just work with that and store each one of our digits there as a symbol. And then where that gets placed in the string, as a text that we would output at the end of the program or input at the beginning of the program, just a long string of symbols, the Unicode or ASCII code, we could do in 4 bits a piece. That would cover all our digits. In the early days of computing, that was important because RAM was a precious commodity. So if we could handle each thing 1 digit at a time and only 4 bits, that was worth it. By about the mid 1980s, the RAM wasn't so precious of a commodity anymore. And we started to have more. Still wasn't like it was today. We don't even worry about it at all today, but we didn't have to worry about the difference between 4 and 8 bits. And the original 4-bit binary coded decimal kind of faded out around then. And then we replaced it with ASCII and Unicode. So I guess we could say this. So instead of the 4-bit ones that faded out 30 years ago, we just used Unicode. So in the early days of computing, there wasn't screens either, right? We never needed to look at those digits. They were all handled internally, but we needed to save RAM. So really it's once every computer had a screen on it so that we also wanted to display those digits, Unicode made a better option than the original 4-bit one, which technically wouldn't be binary encoded stuff, but it follows the same thing because we have symbols for all of our Unicode values. I'm drawing a line. Technically, it doesn't fit in the binary, the BCD was the original 4-bit one. So Unicode is something different. That's 16 bits of a symbol. You might remember or have noticed on those ASCII charts we were looking at last week, which Unicode is an extension of ASCII. Our digits, the digit 0, the symbol 0 is number 48. The symbol 1 is number 49, and they go in order. So the Unicode minus 48 gives us the integer representation of that number. And then we can do the same thing with Unicode, which is ready to print out to screens. It follows that same thing. We just stored the symbol and then calculated at runtime. So that's another one we can work with, usually for really, really big numbers like pi to a trillion digits. Right? We probably need an external hard drive to store an entire, when one number takes an entire gigabyte, we might need some extra storage to work with it, but it allows us to do calculations with that level of accuracy just by calculating the column placement at runtime. Another one that computers really also do is for, well, again, really big and really small numbers. But you might remember in math class, scientific notation. I'll write decimal. In decimal, I remember we would use scientific notation for really big numbers. So if we had, say, 1.7 trillion, which is 1,700,000,000,000, no millions, no thousands, nothing down there, is really that number, which is a whole lot of zeros to write out. If we had to do that by hand or punch zero that many times to put it in a calculator, because most of our calculators don't show zeros, right? There's a good chance a mistake could happen. So we have a shortened way to write that. And in math class, you probably learned we write our digits. We write down the digits we have, and then we count how many times our decimal moves. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to get here. So we write times 10 to the 12th. Another way to look at that, and actually a slightly more accurate way, is instead of all that moving, we have those places like we were talking about, right? We have a 10 to the 0 place. 1, 10 to the 1st, 10 second, 10 cubed to the 4th, the 5th, 6th, 7th, 8th, 9th, 10th. Then over here we have a 10 to the 11th place. And then finally a 10 to the 12th place. So what scientific notation is really doing is saying, okay, 1.7, but that decimal point actually belongs right after the 10 to the 12th column. Which, when we're working with that, you still want to do accounting. Anytime we can switch a math problem to a counting problem, we want to do so. But that's what that actually means. It's which column we're in. Or same thing for really small numbers. So if we had 0.1, 2, 3, 4, 5, 6, 7. So 6 spots over. 1, 2, 3, 4, 5. We want to write our digits down. Oops. 8, 7 times 10 to the, well, we have to move our decimal over 6 spots. But again, we have those columns, 10 to the negative 1st, the negative 2, negative 3, negative 4, negative 5, negative 6. So again, that tells us which column the decimal actually goes after, is what that counting does. And just like we saw with our other numbers, there's nothing special about base 10, so this still applies in binary. 1, 2, 3, 4. So a number like that, 1, 2, 3, 4, 5, 6, 7, and then that, we could write that as 1.0 times 2 to the 7th. It means the same thing. That 1, the decimal actually goes right after our 2 to the 7th column. Or if we have something with the mantis in it, 0.1, 2, 3, 4, 5, I'll just do that one. We could write that as 1.1 times, that doesn't look like times. Times 2 to the 1, 2, 3, 4, 5. So scientific notation just like we're used to. But writing it out like this gives us an extra thing. It's okay if I erase this first half of the board?
Yes.
So, yeah, BCD, what's being erased here is binary coded decimal. We just use our symbol. And for the past 20, 30 years, we got rid of the original abbreviated BCD and we just go with the Unicode symbol. That way that's the symbols work elsewhere too. They're compatible with other stuff. So to do the scientific notation are really big and really small numbers. We use a system called excess K or binary offset. We don't have a 2 to write that multiplication out for scientific notation. So what we do, it'd be nice if we could do all of this part solely in integers. So what we do is we offset by K. And I'm going to write usually K is 127. It's 127 in Windows, Mac, and Linux machines, which Chromebooks are Linux machines. That's Gen 2 Linux. Most people don't go in there and treat it as a Linux machine. They just use the finished version, but we still have all the control like normal. So in our main laptop and desktop systems, that we're going to offset by 127 in order to do this part. So what that really looks like, well, 127 in base 10 in binary, that's 1, 2, 3, 4, 5, 6 ones. 7 more. 64, yeah. 0. They'll leave one off. 1, 2, 3. Oh. 2, 6, 64. Yeah. Next one will be 128. So yeah, that's what that looks like in base 2. So we take this, these 6 bits, and then we have 2 more in front of it to give us some sort of information about like this times 2 part. This is going to get complicated, so this one we just kind of do the introduction, sort of awareness of it at this level. So for a 1 line number, we have 2 more bits we can mess with here to do other stuff. So you can think of that as the times 2 part, is those other 2 bits, and then those exponents we offset by this much, so that this is actually 0. And if we get bigger than that, that means we have a positive exponent, and if we're smaller than that, it's a negative exponent. Did I leave one off? Oh yes, I do need 1 more bit. It is 7 bits. So we have 1 extra bit to cover that part. So then, if we're going to write 1.0 times 2 to the 7th, the number that's over there, 1.0 times 2 to the 7th, we do it in 2 separate parts. So our 1.0, again, we've seen how to do 1. I'm going to write it as a byte here. 0, 0, 0, 0, 0, 0, 0, 1 is a 1 times 2 to the 7th. And then our other part, the 2 to the 7th, well, we offset that by 127. So we do 127 plus 7 gives us 134. So then the second part of our number is what would represent 134. So again, we have the columns, we have 128, which leaves 6 to go. So we don't have any 64s or 32s or 16s or 8s, a 4, a 2, and then no zeros. So a number like this would actually be represented as 2 bytes. One of them is the digits we have out front and how many digits show up in this integer. So I should write the bit type one here. So that whenever we have some, we'll just, whatever bits we have, wherever they're at in relationship to the floating point, we just write out the ones we want. And then our exponent from the scientific notation gets offset by 34. Or if we have really small numbers, so that one over there, the 1.1 times 2 to the negative 5th, and we write out the 1.1 part. So as an integer, so we take both of those and write them out. 0, 0, 0, 0, 0, 0, 1, 1. So we have 2 1s, so we just move our decimal until we get that looking like an integer. And then in the other column, I kind of ran out of room. I'll do it over here in the corner. We're going to offset that exponent by 127. So 127 plus a negative 5 gives us 122. So when we write that out as a byte, 2, 3, 4, 5, 6, 7, 8, we get 128th column. We don't have any of those. 64 will have one of those. So 122 minus 64 gives us 58 left to account for. So we'll have a 32. And we saw the other day that it's a lot quicker to do this going through hexadecimal. What's that leave us? 26. So we'll have a 16. Gives us 10, which would be an 8 and a 2, so we don't have a 4 or a 1. So that's how we would represent that really small number. And notice that on our byte, that first number came out differently. So there's a 1 here when we had a positive integer, and a 0 here where we had a exponent, and a 0 here where we had a negative exponent. So that's how the computer keeps track of the really big or really large floating point numbers. Basically scientific notation, and to handle all of this part, times 2 to some exponent, we offset it by 127. So we are restricted that we can only get up to the 102 to the 127th power, but 2 to the 127th power is a really big number, right? Some of your calculators, if you try to punch that in there, it would give you an overflow. It's a bigger number than the typical calculator can handle. So we just offset it by that much. And then that first bit tells us whether we have a positive exponent, which means it's a really big number, or a negative exponent, which means it's a really small number. And that's where the floating point stuff comes in. This is really the difference between the ALU and the FPU. And a question I've heard before is, how does the computer know when to do this? People have looked at this and like, okay, that pattern looks straightforward. You can see that going through there. How does the computer know when to do this versus a reasonably sized number, right? When we wouldn't have to move our decimal at all. 3.7. That's going to come out evenly in just a few bytes, few bits. 3.75. That's going to come out evenly in just a couple of bits. So we could easily fit that in a byte. And how does the computer know to do this and not just one byte? And the machine doesn't know. The machine always does this. If we have floating point numbers, they will always be handled in scientific notation. And beyond that, it probably gets really complicated. So I'm going to stop there and just say, we just need to know, have awareness of it. There might be a question on the weekly homework. It's labeled as a quiz because it's a multiple choice thing built in Ivy Learn, which is a Canvas product, and Canvas makes any of those things, forces any of those things to be labeled as quizzes if there are questions made right there. But it's just a homework assignment. So it follows like the assignment due dates. You have till the end of the semester to turn that in. It doesn't close like the quizzes do. But the two's complement number is definitely in there, but the question about the BCD and the offset binary or XS 127, those are just the extra questions. This one of the questions on the quiz is pulls from a section in the test bank called other, or the question bank. I shouldn't say test bank. It pulls from a spot in the question, a section in the question bank labeled as other questions. So it's going to pull two of them, and you might get one of these, or you might get a BCD one. So you might or might not see this, but basically just at this level, be aware of it. When we have floating point numbers, they're actually handled in what we would think of as scientific notation from your math class, where we write a small part, where we have a small part, a small number part that's easy to deal with. And then we have another part that tells us where our decimal, where that floating point actually goes. I keep trying to say decimal. Decimal is like slang. It's a short way of saying that. Short way of saying floating point in decimal system. We shouldn't actually say it if we're working in more than one system. But the one that shows us the digits or bits we have, and then scientific notation that tells us what spot that decimal, I did it again, tells us what spot that floating point actually goes in. That's gonna kind of wrap up the binary coverage. I have a couple things in odds and ends, depending on how time goes later at the end of the semester, where there's other things to talk about. One that I think is really interesting is we also have ways binary code is simple enough that we can have it correct itself. If an error shows up, we can make it correct itself, which sounds like something big and fancy. But when I saw that in a combinatorics class, as a math class, fancy way of saying counting, all the math class stuff that can relate back to counting. There was a test question about error correcting codes, and we had to design an error correcting code that would correct 3 bits. So, and that was a test question on a test that covered a quarter of the stuff from the semester. And so there was a lot of stuff on that test. So to write up something that can correct 3 bits, it doesn't take a lot to do it. But it's not on our core learning objectives, so it's just something interesting we'll throw in at the end if we have time. Does anybody have any questions about those other two? Those went quickly. This gets really complicated if you go further, so leave that to electrical engineers on this one. The two's complement, that's what every machine actually does, so you want to be at least somewhat familiar with that. Okay, if I erase this stuff, and we'll move on to the next section. Okay, I assume the silence means yes, or it's okay. So now we'll get back to some doing stuff, because this is some understanding, some content-wise understanding on the binary stuff. We're not going to go work in binary. The separation from computers and technology fields separated from electrical engineering quite a while ago. So the binary stuff is generally left to the electrical engineers. We mostly just need to be aware of it. So now we're going to jump back into some stuff about developing algorithms. The main thing we're doing. Back to the high level languages that we'll actually be working in. What time is it? 3:03, okay. So the second type of the types of tools we need, remember we talked about 4 constructs. We had we need to solve any problem, not just a computer problem, but that's why we're looking at it here. Any problem can be solved with four types of tools. Something to define the sequence, the order we go through, a sequential tool. We need to make choices along the way. That's selection tool. That's the next one we're going to look at. We also need to repeat things, and we also need to invoke things, which means step out of our sequence, do some other stuff, and then come back to the sequence at the exact point we left. We'll get to the others in turn, but the next one there is selection structures. And binary state machines lend themselves naturally to this. And just the name of it, right? If I call a computer a binary state machine, it should immediately indicate, set off some fireworks in your mind about, well, that sounds like selection is going to be easy because everything we do comes in 2 states. So they lend themselves naturally to it, as the opposing states give us a way to distinguish opposing answers. Binary answers. So they answer the yes/no questions. If we ask a question and the answer is going to be yes or no, we say the computer can answer that. What really happens is when we're programming a computer, we define 2 patterns. One of them to do if the answer to our question is yes, and one of them to do if the answer to our question is no. And then at runtime, the computer can determine which one of those patterns it should step through. Machines just repeat patterns, right? Machines are not intelligent. They've built up, and sometimes it starts to seem like they can do stuff. You can call some of them smart devices. We talk about artificial intelligence and machine learning. What machine learning really is we let the machine define what the pattern is instead of the programmer. So the machine does it really, really quick, so it can define more complicated patterns, but it still just follows a pattern. The machine does not have any idea what they are. And a technicality, so another one, a little technicality for those going further. In this class, we will be describing that as yes or no, or sometimes we might want to use the more formal true or false. But generally, when we're thinking about it, we don't use the words true and false in normal conversational English, right? The only time we're going to use false in normal conversational English is we might scream that at the top of our lungs during an argument if somebody tries to make a false claim and we need to silence them very quickly. But we don't actually use those words. So that's the technical term you're going to see all over the writing. But as you're developing your algorithms, it can be a lot more helpful to think yes and no instead of true or false, because we can ask questions. We can ask yes and no questions. And then the technicality for those moving further into software development. In the 2-year software development program, you'll see this. And if you're going on to 4 or 6 years, you'll see it even more. Really, the machine can only answer no and not no. But for here at the introduction level, we're going to call that not no, yes. So the machine can really only answer false and not false. But we can turn our interpretation of those around and call that false and true instead of not false. But that's a technicality that will show up for some of y'all moving forward. But to start off with, it's a lot easier to think true, false, yes, no, those sort of questions. And we saw in the last section, this processing is carried out mathematically. All the processing happens in I'm going to refer back to the ALU every time. Remember, there's two of them. There's the arithmetic logic unit and the floating point unit, but they're essentially the same. So from here on out, whenever I talk about them, I'm just going to say the ALU. I'm just going to talk about the arithmetic logic unit because they do the same thing. We saw that we use 2's complement, and then we can add numbers or add negative numbers and build up all of our math from that. So the machine can follow a pattern and do mathematics stuff. So when we ask questions, they need to be asked mathematically. So that's what we have. We can ask mathematical yes or no questions, which would be more formally stated as true or false. But we use yes and no when we're going through our normal lives conversationally. So that can help a lot when thinking about it, which in the machine, that's going to be a 1 or a 0. Whereas here, that's on and off. Like it's a little bit different if you get fully into the electricity. We define it each time. We could go through a whole bunch of stuff. 1, 0, on, off, up, down, left, right. Blue and red. I'll just use the 2 colors. Things that where our answer is distinctly different. And really we're asking this yes or no question, but sometimes it might be helpful to use these other words depending on the situation. So you want to use the words that help the most with the situation, but we can ask, make these parentheses bigger. That's a side note. We can ask mathematical yes or no questions. So what sort of questions can we ask mathematically? So the answer would be yes or no. Make a little chart here. And this isn't a math class, right? This is computing logic. We keep talking about math, and a few years ago, they did actually rename this class. When I took a class like this in 2011, I think, it was called Intro to Logic. And then at some point after that, they renamed it and called it Computer Math. And when they gave it that label, put that title on there, actually put math in the title, the fail rate went through the roof. Just having that word there made people panic. So then they went back to logic, and people did much better at the class just by avoiding that one particular word. But you'll have noticed we keep coming back and doing math stuff. We're not fully separated from it, but we're not in a math class, we're in a logic class. So when we're thinking about these things, let's think about our questions in English, but do a mathematical comparison so that it helps to, because that's what the computer is going to actually do. That's what the computer is going to do when it runs through that ALU and does some processing. So what are the things we can ask mathematically?
A math problem? No.
What was that, Tyler?
I said, I don't know, a math problem, or in English, like, I don't know, is the light on or is the light off?
Yeah. Oh. So I was looking for the math problems, but in English terms. So
Okay.
just saying a math problem, the first thing we have is, are 2 numbers the same? Okay. Is 2 plus 2 the same thing as 4? Which is equality.
Okay.
So that's one of the yes, no things we can do in math. So all of those. And a side note here, I'll try to write in a different color if this shows up on the screen. 2 or 3 equal signs for equality. We talked about variables when programming already. Did that color show up on the screen? Kind of, it looks like the white. It didn't really distinguish. I guess the angle separates it some. We saw it before when we set up a variable and do our assignment, we use an equal sign. And we read that one equal sign as my variable is assigned this some value. When we want to compare them for equality, we need 2 or 3 equal signs. 3 is used for strict equality. Like right here, our true represents 1. So that means the number 1 is equal to true, but the number 1 is not strictly equal to true because they're different types of things. This one's a Boolean and this one's an integer. So internally, we both represent them as that 1 bit in our first column. So in a sense, they're equal, but they're not strictly equal, and strictly includes type. Or the integer 1 is equal to 1.0, except that one of them is an integer and one of them is a floating point number. So 3 equal signs is strictly equal, so they would not be strictly equal, because an integer and a floating point number are different types of things. All the languages we're working with this semester, maybe one thing at the end, all the languages we're working with this semester, even when we look at some extra ones starting in week and module 5, they're all open type languages, a loosely typed language. So we won't have to worry about types of things. So we won't have strict equality this semester, but in the long run, remember 3 equal signs means they have to have the same type of thing. The integer 1 is not equal to the floating point number 1.0. But right along that, we could ask if 2 things are different. And this is what I meant by the English, the words we want to think about, right? Most of us think in words, not in math. But we need to think about what these questions we're going to ask mean mathematically so that we can tell the computer what to do. And different or not equal, it's fairly common to use an exclamation mark for negation. We want to negate that. So an exclamation mark quite often means not in programming. So different is, we're going to say things are not equal to each other. And then some other ones, smaller, right? In math class, we would say less than. I guess that kind of goes to English, but it sounds funny if we try to put sentences together using less than a lot of times. It's not the natural spoken English most of it that flows out of most of our mouths. And then all our math symbols, greater than, less than or equal, greater than or equal. I'll get down to those in a second. But in English, one of the words, like we'd say smaller or bigger. Or this one especially, the less than or equal to. We would never say that in a normal sentence, right? That's a set of words that only shows up in math class. So in normal English, that's going to be at least. Oh, whoops, that's not at least. The other one, that's at most. Right? If I put something there, x is less than or equal to 5, that's like saying x is at most 5. The biggest number we'll ever get there would be a 5. So in normal English, we would say at most. But then our symbol becomes a problem. Because we don't have one of those on the keyboard, right? We have these, those are just right there on the keyboard, but we don't have one of those. So with computers, we do actually write that out with the two symbols. Less than, equal, greater than, equal, or in English, at least. Right? If you and some friends are heading out for heading out to a restaurant or something and you've never been there, like how much cash should I grab out of the ATM? They're not going to tell you an amount greater than or equal to $20. Whoops, I wrote that backwards. They're not going to say grab something greater than or equal to 20. They're going to say grab at least 20. So more than 20 would be fine, but nothing smaller than 20. So sometimes the English words can be helpful. That's the same reason I was saying, think about yes and no, or any number of binary states that we have in words are probably going to be more useful for the way we speak in English than saying true and false. So be prepared to change the words you're using as you think about and design these selection structures, because using the correct word can make it a lot easier. That's the stuff we can do. You can say, ask if things are the same, if they're different, bigger or smaller, and at least or at most. I have some side notes here. What else did I have? We can also directly put in yes and no. I'm going to write that here, yes and no. Which to the computer, we almost always have the words true and false. The little side note I want to put in there, if the green can be distinguished from the white, is capitalization varies. Sometimes it's like I wrote it here, a capital T and a capital F. Other programming languages might have it all lowercase. Other languages might have it all uppercase. It's usually those three cases. We don't end up with some weird mix. The first letter could be the first letter's capital, could be the whole thing's capital, or it could be the whole thing's lowercase. So you have to know the language you're working in for that. Is it okay if I erase this first type over here? 321. So that's what we can do. Ask mathematical questions. And when generally talking about it, we'll say the computer can answer them, but the computer can't really answer them. The programmer answered them in advance, and the computer can determine which one of those answers we want. So we can ask things like, is 5 smaller than 3? We know the answer, right? The answer is no, but the computer doesn't know that. So when we set this question up in our program, we need to split it off and have both options there. Tell the computer what to do if the answer is no, and what to do if the answer is yes. Because hopefully you can jump ahead. I tried to do something obvious, but hopefully you can fill in a gap here and realize that those would be stored in variables, right? We come up with something nice and meaningful, a good name to keep that in that makes sense in our program. So then we'd be comparing variables, not the numbers directly. But it's an is question. So we have two possible answers. So as the programmer, we have to put both answers together. is 2 plus 2 equal to 4? And again, we know the answer to that. We know it's a yes. But the computer, it's going to make a direct comparison. I tried to mention it briefly. The computer is going to subtract those. It's going to add those two numbers together and then take that minus that. And if the result's 0, then it follows this path. That's probably the last time I'm going to get into that technicality there. But there are two possible answers to that question. So the computer can't really answer it. The computer can identify which one it is, but a computer is not an intelligent thing. It doesn't even know the difference between yes and no. It's like, okay, follow this path or follow this path. And that's what the computer does.
Either on or off.
Yeah. Yes. Exactly. It makes that comparison. And as the result of that on, in which case we follow this pattern. If the result's off, we'll follow this pattern. And we'll spell out what needs to happen in that pattern both ways. And some others. So we could store words too, right? Put the words hello world into a variable, store that. And then later we could ask the computer, does my variable equal to the string hello world? In which case the computer can compare them bit by bit, do a bit by bit comparison and tell if they're equal, bigger or smaller. And I guess, yeah, equal means they're 0. So since we just talked about 2's complement, those going on further, that where you'll have to learn assembly language. If they're equal, we subtract them and the result's 0. So in assembly language, the computer can see that there's a 0 and have an instruction to jump someplace else on 0. So if the result of the subtraction is 0, we have a assembly language instruction jump on 0. If it's not 0, then we have that smaller or bigger. Like we saw in 2's complement, we have that extra bit that we're just going to discard at this level. We call that the carry bit because that's what it does. It carries over to the next column. And then we can jump, the computer can jump to a different instruction based off that carry bit. So jump on 0 or jump on carry is how the machine does this internally. For those going further, might as well throw that out as a preview because that's the actual selection that happens from our processing. The big thing is we're not asking the computer, right? I just said the computer doesn't know the difference. It doesn't know what no means and what yes means. So we're not asking the computer the question, we're telling it to do something. So we're not asking, we're telling. So our keyword is usually so we don't say we're following a pattern. So we don't say is 5 less than 3. We say if 5 is less than 3, then follow one of these patterns. If 2 plus 2 is equal to 4, follow the appropriate pattern. So that gets us into that's going to be our keyword in most of our languages. Yeah, and then the machine can just follow the appropriate pattern. But again, with the words, when we put our algorithms together, we're an intelligent species, so we can handle the question. So for us, thinking about is can be more useful for putting our algorithm together. Now some examples. What time is it? 3:26. So a couple board examples, and then we'll jump over and start doing this in one of our programming languages. I was hoping to do it in both, but we might not get to both of them today. Is it okay if I erase this half? As in, it's okay. There's a video, so you can take a picture of the screen if you need it. I've gone through a lot of chalk today, but they're all small pieces. Did I show you this? Last time I ordered chalk, they just sent a big envelope full of chalk, no box or anything. Not the safest way to ship chalk, but so I have lots and lots of small pieces in there. So we would do something like, so first, for a quick example here, we might say something like input, get some input from a user, maybe enter a number. Just a little segment for the board, probably not a full program here. And we'll use the number they gave us to set a value to X. Yeah, comment in the chat room about the chalk, like, yeah, you got it's. I would much rather go to a store and buy stuff because I can see what I'm buying, not just hope they're going to ship me the right thing. Because in this case, they only kind of ship the right thing. Okay, back to our example. So we'll grab a number from user. I don't know, for some reason, maybe we need this. We need to know what 3 times that number is for something later in our program. Then we'll set another variable to 3 times whatever the user gives us. And then we can ask one of these questions. Is y bigger than maybe 15? And for pseudocode, when I'm writing the thoughts out on the board, I'm going to use curly braces just to distinguish instructions that go together. So our term for that is a block of instructions, so that between this opening curly brace and this closing curly brace, that's our yes section. So if the answer to that question is yes, we'll do all the stuff in here. Maybe output. I'm going to turn that around. Output, that's too big. This isn't a full example, so I just made up some numbers there. So 3 times the number the user gave us is bigger than 15, we're going to say that's too big. So we really want a less than or equal to situation, or an at most 15. But if the answer to that question is no, well, we could stop there, just answer that question, but usually we want to go both ways. Sometimes we don't always need the second part, but I'm going to go ahead and write in the example here. Our otherwise, and our key term for that is usually else. Actually, no. For this first example, I actually wrote otherwise. And then I'll get to our keywords. So is y bigger than 15? It's a yes or no question. So if it's yes, then we'll do this block of code between these curly braces. Otherwise, we'll do something else. Output. That will work. I just kind of made up a sentence to go out there. That's too big, or that number will work. Sort of random, simple, random things. And that's what we want to think about, that asking that question. But again, we're not asking the computer, we're telling the computer. So instead of is, our keyword is usually else, if. Instead of is, we say if y is bigger than 15. So the computer can definitively answer that. So if it is, then it follows this pattern. If it's not, our keyword is usually going to be else. So if it's yes, else, it's no, and that distinguishes which pattern the computer is going to follow. As a binary state, we're going to extend this, probably not till Wednesday when we extend this. So maybe this homework, maybe the programming homework will get pushed back even further. I think the binary stuff will be okay for a couple days. We also have UML symbols. The Unified Modeling Language, our international standard of communication. Is it okay if I erase this slide?
Go ahead.
So our UML symbol or picture for any time we need to make a selection is a diamond shape. So maybe in the case of a flow chart, we're coming down our flow, we have the start up there at the top, and then we get that diamond shape, which represents a selection, a binary choice of patterns the computer could go down, and it splits off. And we'll ask a question. The part that's in parentheses over here goes in here. So like in this case, y bigger than 15 to match that side of the board. And that is either a yes or a no question. And then that gives us multiple branches that our software could take. Makes it a lot more interesting. Our software doesn't do the exact same thing from beginning to end every time, especially if our condition is based on user input. And then whatever the user gives us defines different things. Usually we have more complicated things we want to ask though, right? We want to do something more interesting. Or that's our binary paths, two paths the computer can distinguish between. And this is back to that complicated versus complex. We might have a complicated question we need the computer to answer, something that's actually hard. But machines can't do complicated things. Machines can't do difficult things. Machines can only do simple things. But machines can do lots of simple things. So then what we could do is ask another question. If the first one's yes, what about our next one? And then end up with more branches over here. Have a yes and a no branch over here. So now we have three different paths for that to take. It more commonly goes on the no side. So I'm going to erase this so I don't have to draw. So I don't have to do so much. We can put it either place, but it's much more common to go on our no side. Because we'll ask something, is y bigger than 15? If it is, well, then we know what to do. But if it's not, we could refine that question smaller. Is y bigger than 7? Kind of cut our range in half. If it is, well, then we know what to do because it's between 7 and 15. But if it's not, we could ask another question. And essentially we're doing this. Getting you on that example, cut that in half again, is y bigger than 3. And we end up with multiple branches. And the way the human mind thinks, it usually makes a lot more sense to have something definitive on our yes side, and then our no side, we ask another question. Can I put this in here? So to bring this syntax over here, what this is going to look like is we hit this one. And we'll put that keyword if, and there's some condition where we run through a block of code. That's what the curly braces represent our yes part. But if it's not that, then we get that else part, which if this first block, our yes block is sort of this path on the flow chart, then our else one would be this path on the flow chart. Then what we do is put another question inside of there. If it's this, we'll do some stuff. Otherwise, well, we'll ask another question. And then we can keep doing that. Else, and inside that else, we can ask another if part. And you see how we're putting an if else situation inside of another one. The word for that is nested or nesting. Nesting. With a similar structure inside of the current one, I guess. So the computer can only answer those simple questions for us. When we have a complicated question, we have to build it up we have to build up a complex answer by asking lots of those simple questions. And this one happens a lot. So often that pretty much all of our programming languages have an abbreviation for this. Maybe that's why we usually put it on the no side, because all of the languages abbreviate for that case, where we nest another selection structure on the no branch of the flow of the program. It's okay if I erase this example. That was just kind of leading into the notation. Hopefully that's okay. One last thing I wanted to look right on the board before we get to doing an example. This is so common, we have an abbreviation. So common. We have a common abbreviation. That's supposed to be the letter A. Let me try to make clear. Abbreviation. Oops. And I'll kind of start with something like this. So we have if, and then some condition. I'll put condition 1. And we'll do some stuff. So if that condition turns out to be true, we'll have a bunch of instructions we want to run. But if it's not true, we have that else. Oh, then we do the nesting. We nest an if statement inside of there. We can check something else. I'll call it condition 2. In which case we have an if where we do stuff, or an else where we could do stuff, maybe even put another if else block inside of there. And all of that nesting starts to look like a mess after a while. So what we typically do is bring this part up here. I think it's a little easier if I move the else down in this case. Right, the else if condition 2, and we can just keep going that way. If, else if some other condition, else if some other condition, else if, and then finally way down at the bottom, we get that final else that doesn't have anything listed in it. And that would be our default case. That's common amongst almost all of our programming languages. So we get rid of like the block part and just move that nested one up a level instead of put it in inside and indented. So a little bit of an abbreviation where we can put lots of different conditions to check. And this is what I had in mind for the class example because it covers the simple case lots of times and we can see more in fewer examples. So a common abbreviation we have pretty much everywhere. One of the big exceptions to this is Python though. Is in Python, white space matters. That's one of the things about the Python programming language. An object-oriented language. It's an interpreted object-oriented language with significant white space. So white space matters, which means we cannot have a keyword that's made of 2 parts. We can't have a space in that keyword. So we need to jam that together as one word. And in Python, they went ahead and abbreviated it further so that else space if got combined down into elif. Then we put a condition. So just an abbreviation on that. Otherwise, if and else are the main keywords in Python. So that's the basic idea of those. We're asking a yes or no question. Here's the picture we use for our international standard communication because people all over the world speak different languages. Typically, our keywords are if and else, and we abbreviate the nesting with else if. But in Python, where we can't have the white space there, we usually say elif instead of else if. Does the basic idea there make sense? Anybody have any questions as far as we can ask simple yes or no questions, and if we have a hard question, we can build up lots of simple yes or no questions to get that complicated answer, to get a complex answer to address a complicated question. That's the basic idea. Probably make a lot more sense when we see it in an example, right? I saw your screen light up, Tyler, but you're muted.
Oh yeah, I was thinking of like we're talking about else, but what about then?
Then is another common keyword. So then is the one we use in basic.
Okay.
That goes with it. So actually the then coming down from basic, which I'm guessing you saw in Visual Basic, that's taking the place of the curly braces.
Oh, okay.
If this is true, then do this. So
okay, yeah.
then represents the curly braces.
All right.
Else, if this is true, then do this stuff. Else, if none of that stuff was true, then do this.
All right, you added some gears. Thank you.
So it usually makes more sense to see this stuff. It's an active subject we learn by doing. So probably a good time to go through an example, but we've been at this for like an hour now, right? So maybe another short break. And then I'm thinking, when I was getting ready, I knew there was a lot going on today. So when I timed it, it took, like I was talking and I paused a couple times and it took about a little over 15 minutes, maybe 16, 17 minutes, but should be under 20 minutes, but we've already been at this an hour. So you want to take a 5-minute break before we do the last bit for today, which should be about 20 minutes.
Worked for me. I'm gonna go grab an energy drink. I'm just chilling in the parking lot.
Okay, yeah, I'm gonna I could really use a drink of coffee after talking for an hour straight. So let's take 5. It's 3:48. We'll get back to it at 3:53 and then finish up this stuff for today in the third part. So,
All right.
and I think this module 3 was very content heavy. So this should be the last 2 break day we have this semester. Most of the days will be more active live time at the end, but let's take 5 and we'll get back to it at 3:53. I will see y'all in just a moment.